Okay.
Well, welcome everybody to this second lecture on wood. And this time we will deal with dating of wood, mainly with the help of dendrochronology, but second also a bit of C14. I know my dear colleague Elisabetta Boaretto will talk at length about this method, but there are some connections to the wood science I would like to mention. We have a look at wood last time. We talked about how these plants start growing and become enormous plant bodies. There is a zone inside the wood. As you can see here, you have inside the hardwood, the darker part, then comes the sapwood, the outer part, then comes the cambium, and then the inner bark or bast, and then the outer bark. And if we have a look at the square surface of a tree, then we can see these concentric zones, which we call tree rings. And these rings are the result of growing into thickness year by year. So each year, one new layer is formed around the outside of the stem. So the oldest ring, the first one of the tree growth, starts in the middle, and the latest one is the most outside ring. We talked about age of trees. Some are astonishingly old, like this Pinus aristata from the White Mountains, which has a counted number of 4,844 years, which means we have 4,844 layers countable on the surface of this tree. Now, dendrochronology was invented, so to say, by an astronomer. Andrew Douglas was interested in the sunspot cycle, which was not investigated too long when he started to work on this topic. And he was curious whether this phenomenon was new or it was only not seen before him. And he had a good biological education, and he knew about tree rings, and he thought maybe these sunspot cycles might leave a trace in the ring growth. So he started investigating tree rings. Unfortunately for him, he couldn't find any connection to his sunspot cycle, but he found out that there was a close connection between the climate in the area a tree is growing. And of course, as there are many trees growing, they have all the same impact in the same area, and therefore they have a similar growth. And this was the birth of dendrochronology. Douglas first adopted his method to this settlements of Indians, which have been left for an unknown time before, obviously intentionally, because there wasn't left much for archaeologists to date these remains. And Douglas took samples from the various wooden parts of these houses, and he was able to find the similarities in growth. So he was able to synchronize these various sets of samples. And also he found out that the end of these activities was approximately the same in different settlements. And later on, when climatic research was improved, it was found out that this was a time span of extremely drought. So these inhabitants who were doing agriculture were not able to feed themselves any longer, and they had to move away. Here we have the basic situation for dendrochronology in most parts of the world. For a tree with more than 4,000 rings is only growing in the White Mountains in America. In Europe, trees rarely become maybe 1,000 years old. And if so, they usually have a hollow stem, so the rings of the inside are not preserved any longer. So we had to invent another system of how to go back into the past. Bruno Huber was the one who was studying dendrochronology in America and then went back to Munich, and there he adopted this overlapping method. So if you have one sample growing from the year X to the year Y, you have a certain number of rings with a certain pattern of narrow and wide rings. And if you have another sample, which at least for, say, 50 years has grown parallel to the first sample and then became older, then the two samples, the two sets of data can be counted together. So a mean is calculated. And then, of course, the set of the one sample is elongated by the number of rings the other sample has plus. Another question is, there are different stands of woods. So you have, let's say you have a wood and there is a very dry ridge, and just beneath there is a valley with a small river, and on both sides a tree is growing. So of course the tree on the dry ridge will have much narrower rings than the one growing in the valley with the water. But if we have a look at the overall climatic impact, then the rings in these two sets, in these two wood samples, will be different in absolute growth, but they will be similar in the distribution of narrow and wide rings. So again, if we then switch to this pattern and not to the absolute ring width, we also can use trees and samples from different sites. Otherwise, this method wouldn't have worked. To have a look at the climatic zones, there are, of course, several methods. The upper picture is a very coarse thing. In the south, in red, we have the Mediterranean climate. Brown is the Central European climate, where the left part is more Atlantic. Then the orange is the continental climate, and to the north, we have the subalpine and the alpine or polar climate. If we have a look to Austria, then especially here, there is a much more detailed structure of either the landscape and therefore also for the climate. So if we have a look to the right, there is the precipitation, and you see in the east it's very dry, and in the Alps and in the very west we have quite a wet climate. To the left, the temperature is the average temperature of the vegetation period is demonstrated, and again we have a difference in eastern part, in the alpine part, and in the western part. So again here these climatic areas are demonstrated, and of course the Gulf Stream is one of the most important climatic impacts, and we have mainly westerly winds which drive the several climatic units across Europe. And this is why standards have different reaches. Usually they can only be used quite locally. But for example, and now it depends on the height of the stand of the samples, the higher the larger is the area of possibility to use it. And second, the wood species. If we have a look at fir trees, fir tree wood is to be used on a quite a large area. So the South German fir tree standard can be used in Austria as well. On the contrary, spruce is only possible to be investigated very locally because this tree obviously takes account of the local climate in the first place. So we had a quite a 10 years lasting scientific project, and this was dealing with cedar. Also, our sub project was dealing with cedar. On the overall, this SFB tried to find out about dating problems, especially differences between the archaeological dating and the dating by C14. And so there was a hope that dendrochronology could help to find out where maybe a flaw can be located. Unfortunately, to build a chronology back to the Bronze Age is quite a task, and even 10 years were not enough to fulfill all of this. So, Cedrus libani, of course, has to be first investigated for wood species. So, back to the last lecture, we have the three planes of cutting, the square cutting to the left, the radial cutting in center and upper right, and the tangential cutting on the lower right. And you can see the typical distribution of cells, typically for the gymnospermous wood, the softwood. As you know, cedar is growing in higher elevation in mountains, especially in the Lebanon, in Syria, in Turkey, in Cyprus, and then there is another stand quite far apart at the Himalaya. Of course, the Himalayan cedar is of no interest for our questions, but all others are in the reach for the Levante and could be possible sources for this wood. Of course, there are other softwoods growing there, so it's necessary to tell apart whether it's cedar or something different. And this is important because for dendrochronology, especially for building standards, it's necessary to stick to one certain wood species. Here we have these growing areas. It's the Anatolian, the Syrian and Lebanese, and the Cyprus stand. Before I have forgotten, of course, in Northern Africa, in Morocco, in the Atlas Mountains, there is another subspecies of cedar growing. And again, this is of no interest for our research. According to Egyptologists, most of the cedar wood to be found in Old Egypt was imported from Lebanon. So our first attempt was to study the Lebanese cedars. Nowadays, they only occur on relict stands, which are not like here intended a single area, but rather spots within this pink zone. So the pink zone would be the area where cedars are possible to grow nowadays. But because of deforestation, of goats and sheep grazing in the forests and so on, the wood growth is reduced in this area to a high extent. So it's only single spots where cedars are still growing. There is one interesting hint where in antique times cedars might have been growing, or for sure have been growing. And these are Roman rock cuts, rock marks, which delimitate an area which is shown in green. And this area was called the so-called Hadrian's forests. because the Romans had enormous need for wood to build their ships, they had restricted the use of cedar wood in this area only to the Roman fleet. And these rock marks can be found today, and they delimitate this green area, which is quite large and which is definitely out of the borders of today growth for cedar. Now, for sampling, we have several ways. Of course, the best, but rarely possible thing is to cut a disc. But this means to cut down the tree, and of course, this isn't possible in all situations. So there is the second best thing, to drill a core. You need a special corer, and this is a steel pipe, either with only a certain arrangement of teeth at the tip, or even with a spiral guidance for the wood parts which are cut off in the beginning, and inside the steel pipe a core is going inside, which can then be extracted from the tree and used for studying the rings. Here you have several of these cedar trees in Pshare. There this is a holy grove. A wall was built around by Queen Victoria, and inside it's possible for the cedars to re-establish young seedlings, because cattle is kept outside because of this wall. And there are really gigantic trees growing inside, and it's even not possible for the longest corer to take a sample of all the rings. This is only 120 or 150 kilometers away in Baruch. It's a high mountain, and there trees have a different shape. This is one growing very upright, but there are wind-blown examples, and these show quite different ring patterns. So here I try to take a core from one of these cedars, and here you have examples of already prepared square surfaces of such cores. And you can see the rings, and you can see the patterns, and you can see one phenomenon I have mentioned last time with the charcoals from Katna, which is the change of width. Here you have a very narrow part of the area, then it becomes wider. It's again narrow, it's a bit wider, it's again narrow, it's a bit wider, and so on. Here it's narrow again. So, and as I said, we are still not really aware of the reason of this variability. A second source is dry wood. As we have mentioned last time, we have several possibilities that wood can withstand degradation, and one is to keep it dry. And this is usually inside standing buildings. Here we have the actual roof of this building, and here it is of course possible to take cores with a coring device. Here, this building in Deir el-Kamar in Lebanon has been renovated just before, and luckily all the wood which was extracted from this structure was piled in one room, and we were able to take samples from these pieces of wood. Of course, in this situation, it's not possible to do any research on the building's history of this building. So we can't say whether this part or this part was older and when it was renovated and so on, as all these samples have been without any connection to the building any longer. Another source are museum collections, again dry wood, but of course there it's not possible to cut samples, not even to touch the objects. You can only have a look from the distance. And this is why we had constructed a some machines to allow to measure the rings. This one is a spindle which is driven by an electric motor at the end, and on this spindle a camera with a magnifying lens was mounted, and on the laptop the picture of this camera was shown. And now with the help of the spindle and this motor, we can move the camera along the surface from one ring border to the next one. And the distance the sledge of this device was moved is the ring width. And again, this device was used not only on plane surfaces, but also on bent surfaces, because it was possible to resharpen the lens of the camera. Another helpful device was a flatbed scanner, which of course is only constructed to be working on a office table. So we had to do some refurbishment on the inside to make it working also in these positions. And here, of course, the result were quite magnified pictures of the surface of the wood. As we have said, not only the square surface, but also the radial surface shows the ring borders, and it is possible to measure the distances. So for these pictures, we have created an own program which is able to measure on the picture the distance of the several ring borders. Of course, this has to be calibrated to get correct ring width. Another source is charcoal, as we have mentioned last time. Charcoal comes into existence by burning with lack of oxygen. So if there is a building which is burning, or a big heap of wood burning, then in the inside there most probably is a lack of oxygen, and the result is the production of charcoal. And here in Egypt, of course, it wasn't possible to export these samples, so we had to do the investigations on the site, and we had a grinding device to produce very plain square surfaces, which then had been scanned, and the data we took home. Another source for charcoals was this corridor in the palace of Katna. Here you have the big city with the city walls, and here the area of the palace. And this corridor was overlooked by the excavators of the 1920s and was found only maybe 10 years ago or so. And here you see the holes of the beams of the roof. And the stairs were also covered with wood. And here you had two door lintels with doors inside, and all this was burned, collapsed, and the charcoal was scattered on the floor. We had some C14 data for the first idea, to get an idea about which time we are looking at. So there was one outlier which is far too young for the archaeological ideas concerning this unit, but here we have a datum which is quite fitting. So of course, this causes a problem, because you have two valid measurements, one which is consistent with the archaeological ideas, and one is not. And of course, this sample does exist as well. And you can't just push it away and say, well, let's forget about. You have to incorporate it to your archaeological model, which is not easy, of course. So here we have again this certain sample from Katna, and a magnification of this area is shown below. And here you can see, first of all, these tiny, tiny little rings, and the change from narrow to wide to narrow, and so on. And this is a unique situation for the Levante, of course, we also had a source of wet wood, because in the palace of Katna, there was a well which was completely filled up. And when it was excavated, the archaeologists found big beams or remains of big beams at the bottom of this shaft. So this was some, I can't tell you exactly, but I think it was 12 or 15 meters deep. And in the lower part, there was still groundwater, at least the depths of groundwater coming up. And this cold steam, so to say, prevented the wood from degradation. Another wet wood source was the board, which was found by cavers inside a cave. So this board was used in Bronze Age to put on some vessels, ceramic vessels, which were still standing in place when the cavers found this site. And again, we had some C14, which again shows the same time period. Unfortunately, the trees or the ring patterns from Katna Palace do not fit to the pattern of this board. And again, in Arka, I have mentioned it last time, we had only charcoal samples. There was a tell, here you see it, and on top there was a settlement which was burned down in Bronze Age, and the excavation showed the ground structures of houses, and into these ground structures, the upper parts of the houses were collapsed down, and there was a lot of charcoal and also burned seeds. Here you have some of these beams, and again, you clearly can see the tree rings. And here is the set of the synchronized data of this settlement. And one interesting thing is that several samples have formed, so to say, steps. So this might be, we haven't had a chance for now to look closely to the archaeological record, but it might well be that these were constructing steps within, let's say, the settlement or maybe within a house. Again, another charcoal from Ebla, the famous palace. And this again shows these very narrow parts of tree rings. As I mentioned last time, when these rings are too narrow, it's necessary to do investigations with the help of an electron microscope, as otherwise it's easily possible to overlook such a ring. And this is the result, the preliminary result of this CM2000 project. So we have a recent set of samples which go back to maybe approximately 1300 AD. Then we had a lot of samples from old buildings, from monasteries, from churches, and so on. And these helped to enlonger the modern standard back to approximately 1000 AD. Then, unfortunately, there comes a gap. There are no samples available for now. And then we have several so-called floating sequences. These are sets of samples which fit together, but they have no connection to their neighbors. So there are gaps in between where no ring width are known. And then there is quite a consistent group in the Bronze Age, but this is floating as well. And you can easily imagine it will be quite a task to find samples suitable to fit in these gaps, to bridge the floating pieces together to one single standard. But of course, this should be the final aim, and colleagues in the future for sure will try to do this. It's not only a matter of hard work, it's also a matter of archaeological being lucky, because of course it's necessary to find sites where exactly samples from this time span are available. Otherwise, you won't be able to close the gap. Of course, there are newer methods to try to find the ring patterns and to measure them. One is the computer tomography. Before, it was not suitable to do this, especially the machines available at the hospitals. They didn't show these tiny structures clear enough. But the modern micro CT is well suitable for this task. The only problem is most of the machines are only can only hold tiny samples, so it's not possible to put a coffin inside such a machine. So the standard working place for a dendrochronologist looks like this. You have the measuring machine with the spindle inside, which is turned either by a hand wheel or with a step motor. And then a microscope or maybe a camera with a magnifying lens is looking to the surface of the sample. And with the microscope, you move the sledge from one ring border to the other. With the step motor, we can do it the same. And if it's a magnifying lens, then you see the picture in the computer screen and you move it from here to there. And all these values, the distance the sledge is moved is of course the width of the ring just measured. And the set of these measurements is then stored inside the computer for further working with. This is a, let's say, a typical sample from everyday work. It's a wooden gully, which was found at a fish pond near in Lower Austria. It's made of fir tree. With the help of a razor blade, I have cut the surface and then rubbed the surface with chalk to make it more contrastful. And then this is the surface ready for measurement. And this is the result. You have the red line, which gives the curve, which is how it is called, of the sample. And the blue one is the standard. And now the computer program compares the sample set of data with the standard set of data. What does it mean I have a curve? This is a bit misleading because the most important things are the turning points of this curve, because each of these corners is a measurement of the respecting year. You can see here the years. It's always 10 years between two such lines. And for each single year, the ring width is printed. So as a result, you would have a number of single points. And in the very beginning of dendrochronology, we haven't had such computers and the possibility to do the work here. So it was printed and looked at it on a lighting table. And of course, to compare a point cloud, it's impossible for the human eye. So researchers decided to connect the single points to a curve to make it more easy for the human eye to compare. And this method has been kept through the times. So if you are speaking of a curve in dendrochronology, the most important things are the single corners of this curve, as these corners represent the tree growth in the respective year. Now again, we have here a red sample and a blue standard. And how does now the computer do this work? It is done with the help of programs, of course, and now the program takes the sample set of data, puts it to the end, or let's say to the beginning of the standard, and counts the similarity. There has to be a minimum number of rings, which usually is said to be some maybe 60 years or 80 years if you want to be on the safe side, because below that, there might be a random result. But a pattern of 60 or 80 years usually doesn't occur a second time in the standard. And now the computer program moves the sample for you 1 year to the right, again counts the similarity, 1 year to the right, counts the similarity, until on the other end, the minimum overlap is reached. And in the end, this program has built-in filters, because otherwise you wouldn't be able to work with the results. And these filters only show the most promising results. So if you are lucky, you find one position of the sample which is very, very similar to the standard, and all others are much less similar. Then you can think of having dated your sample, because the standard is absolutely dated. So you know for each ring the year corresponding. And of course, if you find a situation or a position of the sample with very, very high similarity, then you know the year of the last year of the sample. But quite often it happens that as a result, 2 or 3 positions are shown which have more or less similar possibilities. And then it's hard work starts. You have several statistical tests, and the number which is shown here, they can help you to decide whether there is a similarity high enough to say it's dated or not. Then you have the so-called Gleichläufigkeit. It's a percentage of years which have the same direction. Let's start with the beginning of this sample. In the very beginning, we have up to here the same trend. So this year is decreasing in ring width, and this year is decreasing. It is increasing, it is increasing, it is increasing, it is increasing. But here we have a decreasing ring and here an increasing ring. So similarity doesn't mean exactly the same, but quite the same. So there are a few years which are different, but most of the years are the same direction, towards increase or towards decrease. To make it easier visible, the computer program shows these years which have the same trend with a blue background. And you can see from up to here, most of the rings have the blue background. So it's quite promising that until here, it's working. But from here, you can see this background is now mainly black. And it means that from here on, the similarity, the Gleichläufigkeit, doesn't fit, it doesn't work. And then you have to move the sample, the set of the sample, for 1 year to one or to the other side. And usually then this part is fitting and the other part doesn't. And this means here a ring is either missing or it is a ring which has been counted but isn't present. So a mistake with one word. And then you have to go back to the sample to have a look, and you have to have a look at the standard, whether there are lots of samples which have the same situation. If they are, then of course the mismatch will be in the sample, and you have to correct it, and then you can proceed. Maybe you will ask, what's this? This is the so-called skeleton plot. The skeleton plot was used in the very beginning of dendrochronology and is also still used in field work. You take a paper which has millimeter plots on it, and each millimeter is a year, and then you count and say which years are most narrow ones. And these most narrow rings get a mark on the millimeter of the respective year. And you do this for the standard, and you do this for the sample, and then you move the two strips of paper and some position, if it's the correct one, which show a parallelism between these minimum marks. And again, until, well, here we can say until here, things are working well, and from here on there is a complete mismatch. So even here you can see something is wrong in this part of the thing. If you have lots of samples, then you can, of course, calculate the pattern of each of the samples, and then synchronize one by one these patterns. And if they fit, then the final picture would look like this one. And the very important thing is that the minimum years, in many situations, they agree to most of the samples. These are so-called pointer years. In years with a very prominent negative impact on growth, a maximum number of samples is acting respectively, so has a very narrow ring. And now in calculation of the Gleichläufigkeit, you can calculate the overall Gleichläufigkeit, and you can calculate only those years which have been shown to be pointer years. And of course, the Gleichläufigkeit of pointer years has to be higher than the overall Gleichläufigkeit, otherwise something is wrong. And this is the overlapping method I have talked about. So if you start with a modern tree, then you know the age of the last ring. If you take a car today, you know, you will, first of all, you will mention that a ring has started growing. And this is the year of 2022. So the last complete ring is the ring from last year, 2021. And then ring by ring, it goes back. Then you take samples from maybe some buildings, and these samples, usually dry preservation, will provide samples which hopefully overlap in time with the samples before, and then you can enlonger your standard back in time. Here you have some examples from the unfortunately not an existing lab in Stuttgart-Hohenheim. It has been closed down. It was the lab founded by Bernd Becker, whom I was studying with, and who mainly dealt with oak in southern Germany. So he visited all the gravel pits along the rivers. He visited big building sites of water plants and so on. And in many cases, the digging put out old stems, mainly of oak. And these trees were sampled and then put together. And you can see even Bernd Becker wasn't able to find samples, let's say, to connect these floating pieces to one single standard. But luckily, there were other standards in the vicinity. And as a standard is the mean calculation of numerous single samples, then of course the weather impact is a bit more prominent than the single fate of the single trees. And so it's possible also to compare such standards, such big floating pieces. And in this case, it was possible to absolutely date those floating pieces of Danube oak. So again, we have the absolute dating going back to here, of course, with some gaps in between. So the problem of dendrochronological dating is that it is a probability. The result is a probability. And to prove this probability, you have a number of possibilities. So it is Gleichläufigkeit compared with Gleichläufigkeit of pointer years. Then you have the several t-tests. You have the skeleton plot, and you have other statistical features. And all of them together, they are helpful to decide whether you have dated a piece of wood or not. But I have to stress, this final decision is a decision of the scientist doing this. And of course, humans are different, and therefore some are very scrupulous and hesitate to say I have dated it, and others are not, or are less scrupulous, maybe, let's say it this way. So it's always also a matter of how this person acts who is doing this research. Yeah, there are a lot of problems which can produce samples which are not helpful for archaeologists. And then, of course, it's from the side of the archaeologist to determine whether the sample is useful or not. So it has to be certain that the sample belongs to the stratum you want to date. So there are possibilities of an intrusion, of reworking. There are, of course, if you have small charcoal samples, you don't know whether the sample is coming from the inside or the outside of the stem, which is this so-called old wood problem. So even it's the real piece of wood, it is the date is too old. Of course, then there can be reuse or later repair of a wooden object, and this quite often occurs in the Levante and other dry areas of the world, where wood is a very precious raw material, and therefore it can be reused. Then you have an old wood in a new context, or a later repair, then you have an old context with one modern or newer wood. So you always have to ask the question, what do we want to date? And is the sample meaningful in this respect? And of course, if we want to do dendrochronology, we would need to have a sample with an useful number of rings, with a useful tree species, and we have to have a standard for these tree species going back in the times we think the sample is coming from. So sometimes dendrochronology is spoken as an absolute date, but of course there are no absolute dates. It's always a number of uncertainty connected to a date. The only difference to C14 is able to express this uncertainty in a statistical value. Dendrochronology is not possible to do it this way. some possibilities to use dendrochronology. For example, this cathedral has been built, of course, in quite a time span. And if you want to reconstruct when a certain part of this building has been built, you can have a look to posts which have been supporting the boards the workers were walking on, because these posts have been inserted into the wall. And after finishing this certain part of the building, the posts have been cut off, and some remains are still inside the walls. And in course of reconstruction or renovation, these samples can be extracted, dated, and then you know about when which height of the building was reached. Another quite important thing is the dating of paintings on wooden panels, which sometimes have quite a high value. And of course, these wooden panels have been cut somewhere. And in many cases, they were not cut locally, but imported from other parts. For example, Dutch painters liked to import oak boards from Poland. So this is found out by the help of dendrochronology, because if you are able to date it, and if you have available several standards, you can have a look which standard is most fitting to your sample. And then, of course, it's quite likely that the sample comes from the area of this certain standard. And the second thing is that especially very famous painters had a workshop, and within this workshop, lots of painters, of other painters were working, and the head only did the most important things. So maybe he painted the portrait, and the remaining of the picture was painted by somebody else. And of course, sometimes it turns out that such a painting was finished only, but the board didn't fit to the birth dates and dying dates of the painters. So then sometimes it shows off that the painting was finished by some co-workers. Sometimes it was an intentional copy, so it was not said to be an original, but it was a copy of some fan of this painter. And in modern times, unfortunately, copies were made and sometimes tried to be done in the exact way the old painter was working, and then sold to be as originals. And here, dendrochronology can be helpful by dating the wood. Only if the forger is also clever enough to get wood from the times his painting should come from, then of course dendrochronology cannot help. And the similar is with wooden musical instruments. Here again, we have tremendous amounts of money which are paid for such an Amati or Stradivari violin. And here we have also the possibility, with the help of dendrochronology, to find out whether this is an original or only the paper glued into the inside says Stradivari. So luckily, the upper part of this body is made of spruce, and those builders of these instruments had their favorite woods where they took trees from. So usually instruments are maybe made of the same tree, or at least from a very neighboring tree, and the wood patterns of these sets of data are really astonishing similar. So with the help of dendrochronology, such instruments can be dated to a high degree of certainty. There is another aspect of dendrochronology, because as I said, the climatic impact forms the ring. Then of course, vice versa, it should be possible to, by studying the rings, to get an idea about the climate. Of course, this is only to be done in a very rough, in a very coarse way, because a tree is a very integrating living being, and you can only find out about average amounts of precipitation and temperature during the growth season. One method is density measurement. So it is done with the help of X-rays, and these X-rays can then, first of all, they show the ring borders, and second, they also show a degree of the thickness of the cell walls, and these are of course also a hint towards a certain climatic situation. So here we have an example for a reconstruction of precipitation with the help of ring width. You have to, if you want to do this, you have to have a certain time period of measurements of let's say in this case of the precipitation itself, and of course of the tree rings of the very years. And then you divide this time span into two parts. The first part is used to build up a mathematic term which describes the parallelism between the set of ring width and the set of precipitation data. If you found such a term, then you can go to the second time part, and then you try to reconstruct the precipitation with the help of your tree ring data, and then you compare the result with the actual measured precipitation data. And if the result is promising, you can go on. If it is not, then you have to go back and to work on your term. And if it's if it seems to work, then of course you can go to the instrumental time span, and you have only the tree ring data available to reconstruct precipitation. And here you can again see those pointer years I was talking about. So you have certain years where most of the rings of all the samples are moving to one direction, and usually these are decreases. And a similar situation is the correlation between density and temperature. And again, you have to do it the same way I have described before. There are other possibilities to verify your results. So in this case, the investigation of glaciers helps to verify the temperature reconstruction, because usually if the glaciers are coming down, then of course the mean temperature is also more or less to a minimum. And if this has a good correlation, then the reconstruction seems to work. But of course, we have to be aware that the climatic impact is again the result of various very complex situations on the Earth's surface. And all of this to understand and to reconstruct is very, very difficult. Especially these transports of water bodies by fluents in the oceans. It's of high importance, but how it really works, it's not really understood right now. And then there are some oscillations which remind us on these growth oscillations in the wood. But right now we couldn't find a connection between these. So the very famous one is the North Atlantic oscillation, El Niño and the Southern Oscillation. And of course, in the Mediterranean, there are also smaller such situations. And all of this has an impact on the worldwide climate. And all of this is also somehow to be seen in the tree rings if we understand how it all goes together. Now, a very short excursus on C14. With C14, you can measure all organic material. So carbon is a part of all organic material, but it has several ways to come into existence, which is C12 and then C13 and C14. So C13 is C12 is the most common way of carbon. Sorry, and this is here shown. 1 billion of C12 matches a single atom of C14. So you can maybe think of what's going on if you want to measure C14. In the very beginning, it was thought that the content of C14 in the atmosphere was constant, but later research showed that this was not the case. And here we come to the so-called calibration curve. The calibration curve is shown here. These are the so-called wiggles. So here we have a decrease in C14 and then an increase and again a decrease and a slow, short increase. And from where do we know about? We know it from tree rings. So if you have a standard of tree rings, as I have shown before, then you have, of course, a numerous amount of samples. And then you can take these wooden samples. In the beginning, they were taken 10 years by 10 years. And each of such a 10-year sample was measured, compared with the next one. And according to the first theory, there should have been a straight line. But it was not the case. It was like this. And even today, as it showed that these 10 years by 10 years units, they were not sufficient enough to answer some certain problems. Now the labs try to construct a calibration curve, which is year by year. Well, how does a C14 dating works? Just 2 sentences. You have a measurement. You have a Gaussian curve, which gives the probability of the measurement and some other sources of, let's say, uncertainty. And so you have not a single year as a result, but you have a time span. And if this time span is then put in relation to the calibration curve. So wherever these borders are cutting the curve, the absolute dating in years can be given. And this is said here. So 95.4% probability, it's the overall. And with 95.4%, it is between 892 and 1014 AD, which is this big area. But you have to keep in mind, there are some 5%, a little bit less, which are outside this area. So it might be even younger. There is not a very high probability, but it is possible. So this is the problem with C14. Very rare situations occur where the C14 result looks like this. It depends on a very steep part of the calibration curve, because then if you project the uncertainty area to the curve, you get a very short absolute dating time span. On the contrary, in modern times, you have a very flat, a so-called plateau. And in this plateau, you have several possibilities. And this is this ship on the British coast we wanted to date. And we know if it is the ship, it was stranded here. And then, of course, this time span should be the dating time, the building time span. But it is not a good date, of course. And again, connected to wood is a method called wiggle matching. So these wiggles are not only a problem for C14 because of the plateaus and the long time spans originating from it, but they are also an advantage if you take more than one sample from your piece of wood. And if you count the rings between each of these samples, then you know the temporal distance of all the single measurements. And you can put them in a certain program and then project them to the calibration curve. And this narrows down the absolute dating time span to a certain extent. So again, as in wood, we know sample 1 is ring 1 to say 5, and then 10 years, and then comes the next sample and so on. Then we know the absolute temporal distance of the single samples. This is only possible in wood. If it's archaeology, you have the certain strata, and then you can apply a method called seriation. But there you only know the following up of each of the samples and not the temporal distance. So the advantage of C14 is measurements of all organic samples are possible, even micro samples with this new, I missed the word, Beschleuniger. They but they face also some problems. There is a discussion, although the samples are treated with a very coarse chemical puring process, let's say, it is always possible that some of the old carbon is still within the sample. And if it's old carbon, then of course the result will be too old. And if it's new carbon, the result will be too modern. Again, the old wood effect, of course. And again, the problem of the archaeological aspect, whether the sample really belongs to the layer or not. This is a very good example to discuss these various problems of dating. Ramses II was an old Egyptian pharaoh who was buried in one of the graves in the Valley of the Kings. If you think without knowing the history of all of it, if you want to date it, you first would think maybe the body of the king would be most promising. But besides the problem that, of course, this is not possible, the body was mummified, not only with 3 resins of those days, but also with some material which contains very old carbon. So it's petrol coming from the earth. And of course, then if you would take a sample of the skin or so, then even then even though it is a part of the body of the king, it would be a wrong date. So the only thing I could think of is to extract one of the teeth, and inside one tooth, there is a so-called closed context, because it is a very hard material, very difficult to be penetrated, and the inside material is not altered or changed anyway. Well, is it possible to take those linens or maybe the coffin for dating? If you don't know the history of all of this, you would think, yes, it is. Unfortunately, it is not, because this mummy was put out of its original grave by ancient grave robbers and was reburied by a later pharaoh who used a new coffin that new at that times, and also partly new linen. So if you take samples from these, you might get an idea of the reburying time, but not the actual time of Ramses' death. So you can see the history of a sample is most important to get a datum which helps. For dendrochronology, you'll not always get a datum, because sometimes the pattern of the sample and the pattern of the standard doesn't match at all, and then you don't have a date. Of course, C14 gives a result in each situation, but whether this result is an answer to your archaeological question or not, it's your decision. So, coming to an end, what do we have inside a tree? Well, first of all, we have an archive, because this tree has been wounded in this year. The wound has been closed, and more outside, it doesn't show any traces any longer. That's one thing. So you can, for example, do fire history with the help of dendrochronology. What do we have else? We have the hardwood and we have the sapwood. The sapwood is easily identified by the numerous holes of insect larvae. And here we have the so-called veiny edge, which is the year the tree grows just before he was either dying or was cut down. And of course, this ring is the most important ring to our purpose, because we usually don't want to know when the tree started growing. We want to know when it was cut down, because cutting down is maybe near to the time of use of this wood, and the time of use of this wood is maybe near to what we want to know archaeologically. So the veiny edge, if it is present, is most helpful. And if you decide to take samples, you have to have a look whether somewhere, if you have a tree trunk or if you have a post, somewhere this veiny edge is present. Sometimes it is not present, but it's only a part of the sapwood you find. Then, of course, you can have a look at the tree species, and you know approximately how many rings of sapwood usually are growing in a certain tree species. And then you can calculate or assume how many rings are missing, and you can approximately say something about the cutting down of the tree. Most common is the situation here. There is some outmost ring, and you don't know how many rings are missing to the veiny edge. Then, of course, you can only give a datum post quem, which means cutting down has been some years after the year X. Okay, so if you have a piece of charcoal of a burnt palace and you date it, what is the result of this action? What does this date tell you? Does it tell you the burning down of the palace? No, it does not. It tells you anyway the date of building it up, because it's still the construction wood. So it's only transformed to another condition. So dating wood always dates the death date of the tree, if you have the veiny edge. And of course, dating anything else always tells you that the age of the certain sample. So if you have a pot with burnt seeds inside and you date the seeds, you are dating the seeds. And if you compare the dating of the seeds with the archaeological dating of the pot, then it might fit or it might not. And again, then you have to find a solution. So please be aware, you always date the death of an organism, whether wood or some other plant, and all archaeological results are an indirect conclusion with all the uncertainty of either the measuring method or the archaeological attribution. So what was Jean-Paul Talman speaking? The closed context is the most important thing in archaeology, because only then you can be more or less sure of the correct attribution to the sample, of the sample to the archaeological unit. Well, and this, I hope you can use one or the other thing of this lecture for your practical work. Unfortunately, I can't see you, but maybe Mark can allow to hear you, so we can have some discussion